Alright, so here's our fifth lesson for modern physics, and we're getting into quantum mechanics. So, just to recap, we know that light is a wave. Young proved that with his double slit experiment, and then that was further proven by Maxwell's combining electricity and magnetism to show light's an electromagnetic wave. So, without a doubt now, light's a wave. Sorry, Newton. Huygens was right. So let's get into, here we go, something called blackbody radiation. So in the early 20th century, Max Planck was asked to improve the efficiency of a light bulb. Now, when I say light bulb back then, the only light bulb was the incandescent light bulb, which means it heats up to a certain temperature and glows. Now, this is a pretty cool effect because, I mean, this is how we can determine what the temperature of a star is, because stars are different colors. Right? And if you look over here, let me get my pen. Look over here, if something is glowing at, say, 2,000 degrees, it'll be a reddish color, 4,000 degrees, yellow color, 10,000 degrees, a bluish color. Right? And that can help us with stars. This is also true for like elements on your stove element, right? When they get to a certain temperature, they start to glow. It doesn't really matter what the object is. If an object heats to about 2,000 degrees, it will glow red. Doesn't matter what it is. Okay, and this is called blackbody radiation. And so he needed to sort of improve on the efficiency of a light bulb. To do that, he really needed to understand blackbody radiation. And unfortunately, at the time, nobody really understood it. Let me explain why. Let's say you have a cavity. So here I have two cavities. So there's 1 and 2. Now let's say at the walls we have atoms, right? And atoms have electrons, and if they're heated, those electrons can vibrate. And at the time, people thought that, well, waves which are emitted are continuous, right? This is classical physics. Waves are continuous. They're not broken, they're continuous. And because they're continuous, when an electron is heated, and let's say it moves from, well, they haven't come up the idea of orbits yet, but it moves from a different position from the nucleus. Well, they thought it would move continuously from one position to the next, and therefore it could emit light in all frequencies, and every frequency has an equal chance of being emitted. Well, if we look inside this cavity, notice that we're going to start at a wall, and that's going to be a nodal point for the electric field, just like in grade 11 waves, a fixed point was at produced a nodal point. And if you have a certain wavelength, let's take a long wavelength. So here we have a long wavelength, one wavelength right there. Okay, here you have like 1.5 wavelengths. Here you have half a wavelength. Okay, so they end at another wall, which would be a nodal point. And there's only certain configurations you can do to be able to fit into that cavity. So you don't get many electromagnetic waves that way. However, the shorter you make the wavelength, just like in number 2, whoop, what did I push? Just like in number 2, the more possible configurations you can have for that wave. And so because of this, they assumed that in classical theory, the shorter the wavelength, well, the greater the intensity. In fact, they thought intensity had to do with frequency squared. So let's say you heat up something to 5,000 degrees. Well, as the wavelength gets shorter and shorter and shorter, and I'm not drawing this well, but the intensity just blows up. Now, this is not what actually happens. This is what classical theory predicts happens, but thankfully it doesn't happen, because if you turned on your stove element, well, technically that stove element should blow up to gamma rays and should just destroy every single house and living thing in it. Luckily, it doesn't do that, right? What happens is, when it gets to the ultraviolet range, it drops, and then drops and drops and drops. And nobody understood why this happened, which at the time was called the ultraviolet catastrophe, right? Because predictions just completely dropped off with experiments. Well, so in desperation, Planck just decided he would try assuming that these energies come in packets, right? The electron can't release continuous energies, it must release packets of energies. It was more of just a last result, didn't know what else to do, so why not try it? Right? See if the math works, see what kind of predictions you get from it. And when he did that, his predictions perfectly matched with experimental results. And he determined that the energy of these packets, which he called quanta, okay, quanta just means a packet, okay, don't get scared of the word quanta, it just means packet. Okay, these packets of energy, or these quanta of energy, are proportional to the frequency. And the proportionality constant, which is now named after him, Planck's constant, is 6.626 times 10 to the minus 34 joule seconds. Now we can rewrite HF as hc over lambda, because since these are electromagnetic waves, they travel at the speed c, and the universal wave equation tells us that c equals wavelengths times frequency, so we can replace frequency as c over wavelength. And this was the beginning of quantum physics, a study that so many people worked towards but hated. Why did they hate it? Because every single result they came up with was completely opposite than what common sense would have told them. All right, so let's try the first question. This isn't so bad. It says calculate the energy of a quanta of red light. So I'm going to make this bigger. Bam. All right, calculate the energy of a quanta of red light. And the wavelength is 635 nanometers. So we have E equals Planck's constant times the frequency, but since they don't give us frequency, they give us wavelength. I'm going to replace that with C over lambda. Now, when I plug this in, so we have 6.626 times 10 to the minus 34. We have the speed of light times 10 to the 8. Yes, I'm leaving out units, I'm lazy. Don't leave them out at the very end. And then we have our wavelength, which was 635 nanometers. Put it into meters, so 6.35 times 10 to the minus 7 meters. Okay, now you can put in units to make sure that you get joules in the end. You do. This is joules seconds. This is meters per second, so your seconds cancel. And then you have meters and over meters. So meters cancel. You're left with joules. Specifically in this question, 3.13 times 10 to the minus 19 joules. Okay, this seems like very little, but remember it's from one quanta of red light, which later we're going to call a photon. But the term photon was derived from Einstein in the next experiment that we're going to do in this lesson, and the simulation that I'll be assigning tomorrow. But because it's so small, physicists decided to come up with another unit of energy when dealing with atoms and anything quantum mechanics. Quantum mechanics just means the mechanics of, well, packets, right? And packets is always around when we deal with things that are very, very small. And so this is the physics of the small. Now let's go back to electromagnetism. Remember parallel plates? Let's say we have parallel plates and we're going to take an electron and we're going to do work to move this electron across a potential difference of 1 volt. Well, what work is done? Well, we know work is Q times delta V, and the charge of an electron is 1.602 times 10 to the minus 19 coulombs times 1 volt gives you 1.602 times 10 to the minus 19 joules. And what physicists decided was, well, let's take this value and set it equal to 1 electron volt. And that's units of energy, and 1 electron volt is exactly equal to 1.602 times 10 to the minus 19 joules. So if we were to take this and divide it by 1.602 times 10 to the minus 19 joules per electron volt, right, we will get how many electron volts this energy is, which is 3.13 minus 19. Is 1.95 electron volts. So that's a number that's easier to work with. Okay, let me go back to the PowerPoint. Oh, I did it in the PowerPoint. There you go. All right, now let's go to another experiment that people were having trouble understanding. So Heinrich Hertz was doing this experiment. Now this is a gold leaf electroscope. You might remember them from grade 9 electricity, where we used an electroscope to determine whether or not something had a charge. If it had a charge, right, these two would have the same charge, and this gold leaf here would be repelled from this one, and they sort of move apart like this. Okay, so in Heinrich Hertz's experiment, he gave it a charge. So there's a charge. Let's say he gave it a positive charge. It doesn't matter if they're both positive or they're both negative, they repel. Okay, so this electroscope determines whether or not there's charge. So right now there's charge. He gave it a positive charge and then shined red light on it. It says laser, but they didn't have lasers yet, so red light. Shined red light on it. Nothing happened. The charge stayed there. Okay. Gave the plate a negative charge. Did the same thing, shined red light on it. Nothing happened. Plate stayed there. All right then. Now took ultraviolet light. Gave it a positive charge. Shined ultraviolet light on the electroscope. Nothing happened. The gold leaf still remained repelled. So the charge is still there. Then gave this plate a negative charge. And when he shined ultraviolet light on it, the leaf dropped, meaning the charge somehow has left the plate. This was curious because he did the same thing with red light with negative charges. And so he went back to red light and this time tried it again. The charge didn't leave. So he increased the intensity of the red light, made it brighter and brighter and brighter and brighter. No matter how bright he made the red light, the charge remained, didn't escape. This was confusing. Right? If light is continuous, which it is, right? It's an electromagnetic wave, and that's just continuous. And if it's continually hitting this plate, then it should be continually transferring energy to that plate. And if I make the intensity greater, well, then it should be enough to cause the electrons to jump off the plate and the charge to drop. Why is it not happening? Along comes Einstein. Einstein says, well, let's look at what Planck did. Planck came up with this idea that energy comes in packets. Well, what if light energy comes in packets? If light energy comes in packets, it doesn't really matter if you're shining greater intensity of red light at it. It's not going to cause any electrons to escape. Think of it this way. Let's say I have cookies. Let's say I have a bunch of cookies. And we have all sorts of people in the class. And in order for them to have enough energy to leave the class, person A requires 5 cookies. But this person is very picky. If I give this person 4 cookies, they're not going to accept it. They want 5 cookies. If I give them 3 and say, just have these now and I'll give you 2 later. No, I want 5. Right? Okay. It doesn't really matter how many cookies I wrap in a little package and pass them, unless that package has a minimum of 5 cookies, they will not be happy. They won't accept it. If I throw them a package with 4 cookies towards them, they'll just move out of the way. They don't want 4 cookies. Okay? I can start having 100 packets of 4 cookies, increasing the intensity, and start like throwing them. It doesn't matter. They'll be able to dodge every single one of those packets until I put 5 cookies in a package. So he showed that light comes in packets. Well, wait a minute. Doesn't that mean light's a particle? I thought we've already had this discussion. This is a couple hundred years old debate about light being a particle or a wave, and then Young proved it was a wave, and Maxwell and Faraday showed it was an electromagnetic wave, and now we're back saying it's a particle again? Well, yes, I guess so. Right? This is kind of interesting. So Einstein's saying light is a particle, and he's calling these particles photons. And since this effect has to do with electricity, he calls it the photoelectric effect. And this explanation of the photoelectric effect is what won Einstein the Nobel Prize. Not special relativity, not general relativity, the photoelectric effect. I know, right? It is a very, very important effect, but why didn't he win one for general relativity? That also showed us gravity's been wrong the past couple hundred years as well. But, all right, he should have got 2. But let's look at the photoelectric effect. Now, I put some statements here. I said to emit photons, you need a certain amount of energy. And since energy is proportional to frequency, you need to have a minimum frequency in order to emit photons off of a metal plate. In order for photons to emit electrons off of a metal plate. Okay, so we called this frequency the threshold frequency. And the threshold frequency is different depending on what material it is, right? The different structure, the different atoms, the different hold those atoms have on their electrons are all different. So that threshold frequency is different depending on the material. And he called the amount of energy required to emit those electrons would be equal to h times the threshold frequency, which he called the work function right here. That's not work done, it's the work function. And we have a chart here. This chart's also in your textbook. I think I took this directly from your textbook, which says for different materials what their work function is. And this is all in electron volts. Okay, you have to be careful with this equation because this gives you something in joules and this is an electron volt. So you need to switch either joules to EV or your EV to joules, right? You can't subtract joules from EV. All right, well, what about all that extra energy? Let's say I threw a packet of 6 cookies at someone. Are they going to take it? Yeah, they're going to take it. They wanted a minimum of 5. Those 5 cookies will get them out of the room, but that 6th cookie gives them additional energy. And it turns out that additional energy is kinetic energy. Okay, so before moving on to this problem, let's go over how this looks like. All right, so this is the photoelectric effect. Now here I have sodium. This metal plate is sodium, and I'm going to shine red light on it at an intensity of 20%. Now it doesn't matter if I bring this up to 100%. If nothing's coming off at 20%, nothing's going to come off at 100%. Okay, well, let's bring this down then. And instead of increasing the intensity, let's increase the frequency. Now, as I increase the frequency, nothing's going to happen until you reach, there we go, the threshold frequency. All right, so here we have the threshold frequency. We're getting these electrons emitted, and it's going across to the other plate, which will produce a current. But here's the question. What happens if I increase the frequency even more? Do you remember from that equation? If I increase the frequency more, 6 cookies instead of 5, we're going to get additional kinetic energy. So these electrons are moving faster and faster. Okay, now why are some not moving the same speed as others? Well, think of what we know about the atom at this point. Those electrons are in different orbital levels, and in order for them to escape, completely escape, well, the ones in the higher orbital levels require less cookies than the ones closer to the nucleus. Therefore, if we can get the frequency high enough so that we can get electrons from different orbits escaping, well, those different electrons will have different amounts of kinetic energy left over because they have different amounts of energy required to escape. But let's not focus too much on that. Let's focus as to what's going to happen now if I increase the intensity. Does anything happen? Think about it before I do it. All right, let's try it. What's happening? It's a lot more of them, isn't it? I mean, the kinetic energy hasn't increased. Right? It looks like the energy of the electrons being emitted is about the same as before, but we're getting a lot more emitted electrons. Okay, so that's what intensity will do. It'll increase the number of electrons being emitted as long as you are above the threshold frequency. All right, so this is called the photoelectric effect. Let's go back to the PowerPoint, and we're going to do question number 2. Question number 2, we have orange light with a wavelength of 600 nanometers, or 6.0 times 10 to the power of 2 nanometers. It is directed at a metallic surface with a work function of 1.6 electron volts. Calculate A, the maximum kinetic energy of the emitted electrons in both joules and electron volts, and then B, the maximum speed of the electrons. Okay, let's start with A. So our equation is the kinetic energy of our emitted electrons, which are called photoelectrons. There's nothing special. A photoelectron is no different from an electron. We're just specifying that these electrons were emitted from a surface due to photons. Okay, their kinetic energy is going to be equal to the amount of energy that the light gives them, subtracted by the amount of energy that was required to escape. Right, so this doesn't give us anything in frequency, it gives us wavelength, so I'm going to change this to hc over lambda minus w. Now we have 6.626 times 10 to the minus 34 joule seconds times 3 times 10 to the 8 speed of light, that's a terrible 8, over the wavelength, which was 635 nanometers, so turn it into meters, 6.35 times 10 to the minus 7 meters. And then we're going to subtract the work function, which was 1.6 electron volts. Okay, remember I said you can't technically do this. This gives you joules, and this is electron volts. So what I'm going to do is I'm going to put it in SI units. To start, I'm going to change electron volts into joules by multiplying it by 1.602 times 10 to the minus 19. When you do that, you'll get an answer of 7.45 times 10 to the minus 20 joules. Now, if you divide that by your conversion, 1.602 times 10 to the minus 19 joules per electron volt, you'll get 0.468 electron volts. Okay, so that's our kinetic energy. Now, part B says to change that into, not to change it, to find out the speed of those electrons. Well, to do that, I'm not going to work with electron volts. I'm going to work with joules. Okay, so if this is our kinetic energy, we also know that kinetic energy is 1/2 mass times velocity squared. Rearrange for velocity, we get the square root of 2ek over m. So now we plug in 2 times our kinetic energy, which was 7.45 7.498. Did I write it wrong before? 7.498 times 10 to the minus 20 all over the mass of an electron, 9.11 times 10 to the minus 31 kilograms. Okay, and when we solve this, actually I might have it in the PowerPoint. .07 times 10 to the 5 meters per second. And we're perfectly correct in doing it this way. As you can see, this doesn't approach any relativistic effect at all. Okay. So moving on, there's one last thing I want to mention, and that's the Compton effect. So Compton took this photoelectric effect a step further. Instead of shining higher energies like UV onto a plate, he went even higher and put X-rays. He showed X-ray radiation onto these plates. And what happened was he got, let me show you here. So here we have an incoming ray of light, which is high energy X-ray. And when it hit the plate, we ended up with an electron being emitted in this direction with a certain energy, and another wave of light being emitted in this direction, which was a lower frequency. Okay, so a lower energy X-ray. The really cool thing was that in that collision, both energy and momentum were conserved. Okay, that we'll get into a little later when we go into particle physics, but really cool effect. Also, I mentioned this earlier in a previous lesson that you can determine the momentum of a beam of light, of a photon of light, even though it has no mass. So let's start off with P equals mv. Okay, right here. Momentum equals mass times velocity. Well, due to the mass energy equivalence, we can replace m with E equals c squared. Okay, so here we now have momentum equals this, okay, where 1c can cancel. So momentum equals E over c. Now we know what E is. It equals hx. I'm having trouble speaking today. It equals h times the frequency, okay, for a photon. So we can replace the energy, which h times the frequency, and c, using the universal wave equation, we can replace that with the wavelength times the frequency. Frequency cancels, and you get the momentum of a photon equals Planck's constant divided by its wavelength. Okay, so that's it for that lesson. But it is cool to think about what quantum mechanics has brought us, right? LEDs are based on quantum mechanics. Solar panels are based on quantum. Lasers, right? The transistor, which led to all sorts of computers and the internet, right? The MRI, which we are going to be doing an experiment on later. The transition electron microscope, nanotechnologies. Quantum mechanics has really changed our world. But of course, it always bothers me when someone discovers something new and people ask, well, what's that going to do for us? What does that mean? Well, imagine asking Max Planck, who finally figured out why light bulbs glow a certain color. And they ask him, what does that mean for us? How is that going to help us? You think he's going to say, well, there's something called the internet that we're going to come out with pretty soon. It's like, no, you can't really make that connection, right? But once you understand more, you'll be able to use that understanding to build more. All right, see you next lesson.